Hey, everyone, this is John Avina. Thank you for coming to our show. Hey, today we had advertised previously that we were going to do something on boilers, electric boilers, decarbonization and all that, or what is it, electrification and boilers and all that. And the guys who were going to do it, they had a good reason and they said that they didn't want to do it. But I got them, I think they're coming back in February. So sorry about that, but we're doing another one on chillers. We did chillers last month, and we have never had a response like this before. I mean, we had so many people who wanted more information and links to the show or the PowerPoints or whatever that we brought Duane back. And this talk he's going to give is going to be I think more elementary than the one we've seen before. So for some of you who thought that the last one was a little detailed, this will be more up your alley. But anyway, before that, before we get started, as you know, we've trained you all to come in late. And as we're waiting for you all to come in late, we usually say something that might be entertaining or might be annoying. I don't know what. And today, Clay Barkley is going to speak. He is an energy engineer here. He does energy audits, and he found something amusing in a building he was recently at. And so, Clay, go ahead, tell us what you got.
Yeah, so I've been doing this about 12 years. This is the first time I've seen this. There was a commercial property in San Francisco. It has a flat roof. It's an event center on the first floor, and second floor there are 24 living units. And the occupant complaint is that it just gets super hot in the summer. So I took a IR camera and went to the building because they didn't think they had very good insulation. And it's 65 degrees when I was there.
65.
I asked for
that's not very hot.
It's not very hot. And I asked for drawings ahead of time, like you always do, and the drawings called out R30 bad insulation and a couple of 5/8 gypsum board ceiling. I was like, okay, well, got there, and this is their ceiling. It's just exposed truss. There is no gypsum. There is no insulation.
No.
So I headed up to the roof, and they got the asphalt rollout type. And it's the average was 131 degrees on the roof.
Wait. So let's back up. It's 65 degrees outside. His roof is 131 degrees. That is crazy to me.
It's pretty chilly. It's in direct sunlight for most of the morning and afternoon. So it was about noon, but yeah, it was not a hot day. So yeah, then I've never really got to do this, but I've always heard you can find potential roof leaks based on temperature differences with an IR camera. And he said he had a leaky roof, and there were a couple spots. You can't really tell just looking at it, but when you look at the temperature difference, so this dark blue is around 90, and then this spot is around 145.
It's dark because there's moisture in there. Is that why? There's water in there?
Yeah, so moisture has gone under the roof and it's kind of just sitting there absorbing the heat, so it's a lot cooler than the roof. So there's a couple spots of that I found pretty interesting, but then the real interesting part is they had this coat on like white patch that they had patched the roof for another roof leak, and so this box, it was an average of 80. And the other box that was not patched with the white patch was 137. So it's kind of a proof of concept that the cool roof is a lot cooler.
Now, but wait, this wasn't a silver roof, right? It wasn't like reflective, so that your flare wasn't was like measuring things funny.
No, I just think it was the white coat on, paint on stuff.
All right, but now, didn't you have a screwdriver you're going to show us or something like that?
Yeah, I'm getting there. No, so impatient.
Okay.
And then, so yeah, this is the second floor ceiling. It's basically just 1x6s, and so their ceiling temperature is 114 degrees, around the same time as it's 135 on the roof. So eventually, I asked him if I could stick a screwdriver in between the two 1x6s, and he said I could. And so I jammed it up there, and there it is popping out on the roof. There was no insulation. There is no insulation, I guess. That was my San Francisco story.
All right. Yeah, I thought that was kind of cool. So one of the things he showed when he first showed it, I asked, well, wait a sec, you just put a hole in the guy's roof. I mean, who's going to pay for that? Can you explain that? You don't just go put holes in people's roofs. Clay?
I mean, I asked him if I could do it. He said, yeah. And I just told him to, go to Home Depot and get some Henry's all wet patch or whatever that tar is called that I've used on my own roof in a rainstorm, and kind of just slather it on, and he's good to go. He said this was the least of his worries about his roof. So go right ahead.
Okay. I thought that was really amusing. Okay, so that's enough for being amused. I guess that took a little longer than we expected. Clay, that was cool. Thank you so much for doing that. All right, so today, again, I'll mention, we are doing chillers, not boilers, not electrification. We are doing chillers. We did chillers last month with Duane, and people liked it so much, we brought him back. A lot of people, not a lot, but a few of you said, why did you stop? You should have just kept going, and if people had to leave, they could leave, but we wanted to keep watching. Well, okay, we got him for another hour. So let's go to it. Duane, why don't you introduce yourself? Because you can do it better than I can. And another thing is, if you could tell us, or just give us like a 3-minute brief on what did you talk about this last month, and what are you going to talk about this month, and why is it different? So then people know what we got coming to it.
Sure. I'm the engineering director within JLL for energy sustainability and services. I've been doing chill water system optimization for around 30 years or so. I have a patent and a trademark in it, and I regularly do training within JLL, and I do training outside of JLL within our client group typically. Sometimes you'll catch my accent. I live in Texas now. I've been here for about 15 years, but I'm originally from Canada, so you'll hear me talking like a Minnesota boy once in a while. And so what's different now from our last show? So the last time we went through this, we went through an awful lot of stuff, and I want to kind of slow down in a couple of areas and spend a little bit more time talking about load side management and condenser water operations. So we're gonna move into that in a little bit more detail, and about why we do things the way we do and why they're important. Also going to talk about some steps that you need to take initially when you're before you start implementing this stuff. So we're gonna be verifying conditions, looking at load side operations, tower side operations, some work with equipment staging, look at that. And then we're also going to look a little bit at fault detection. And just to kind of come full circle with this, one of the things that we're looking at, just to give you an idea about why we do it and what difference it makes. This is from a data center that we went through, and you can see right around 8 o'clock in the morning, the plant all in went from around 0.82 kilowatts per ton down to around 0.48. That's the blue line, and the temperature varied somewhere between 68 to 72 on the floor. The ambient temperature during that time went from around 70 to 82. These are with air-cooled chillers on this job. The interesting thing about this one was these are 500-ton chillers. We were running with 2 chillers up top, and when we finished process, we had a 600-ton load, and we were running with 1 chiller quite easily. It was running around 75%, something like that. So 500-ton chiller with a 600-ton load. That's all right. The delta T went from 8 degrees to 15 degrees. The design was 12 degrees. It was a 12-degree design. And just so you know, what we were doing was we were changing the delta P set point a little bit at a time. And as we changed the delta T set point, or delta P set point, the delta T in the system went a little bit broader, a little bit broader, a little bit broader. And then we reached a point where the change in differential pressure set point didn't make any difference at all in delta T. We were down around, at that point, we were down around 5 PSI. And it just didn't make any difference at all in the delta T. And so there wasn't any point in going any lower. That's the commissioning step, the last commissioning step in the load side. So what we want to do Well, is we want to get rid of some system inefficiencies, and this is a function of PID control. PID control is a response generated control algorithm, PI control. Something happens, you make a response. The system tends to over respond, either too much or too little, and then it looks at the error from what its output was to what it was supposed to be at, and it starts to make changes in that response. So there's always some overshoot and undershoot in PI loops, and that results in some wasted energy. That wasted energy accumulates as you go through the system. It accumulates at the pump, at the chillers, it eventually finds its way out through the cooling tower. And what we want to do is we want to find a way to siphon that energy out and reduce the amount of overshoot and undershoot in the system. And we're going to do that in some ways that are pretty simple. Again, we're going to start with new construction plants generally run around 0.4 to 0.5 kW per ton. And retrofits, when we see them, they start out somewhere around 0.95. Some of them we'll see up around 2 kilowatts per ton, but it's pretty typical to see an existing plant running around 1 kilowatt per ton. And we want to get that down to somewhere in the range of around 0.45, 0.65 kW per ton. That's the goal. First step in the process is to verify conditions. So optimization is not going to fix equipment that is in bad condition. So we want to verify the cooling tower is reasonably clean and operates properly. If you've got busted up fill or you've got spray heads that aren't working, optimization is not going to fix that problem. Same thing with chiller condensers. Doesn't have to be spotless, but reasonably clean. Chill water system, we want the chill water to be, again, reasonably clean. Doesn't have to be spotless, but if it's black and thick and gooey, that's not a good thing. We want, kind of got to get that fixed up. Want the chill water pumps to be working and the VFDs to be working properly. And we're not going to put any additional strain on any of these devices. In fact, they're probably going to work less harder than they used to. But going through optimization and having equipment fail because it's not working properly is more complicated than it needs to be. So it's better to have the system in reasonably good condition before you start. Same thing with condenser pumps and VFDs. You want them to work properly in reasonable condition. And on the chill water side, we want to remove as many chill water three-way valves as you can. Either remove them or isolate the bypass leg. And that's because we don't want to have a lot of unused chilled water pumping out of the chiller plant and coming back. We want that any kind of water going out of the chill water plant, we want to be using it for cooling purposes. Now you may come across situations where you have one or two chill water valves, three-way valves at the end of a loop. That's no big deal. You can leave them in. One or two here or there isn't gonna break the bank. At the air handler, we have an issue with log mean temperature difference that we want to pay attention to, and this is one of the things that's kind of important. So a cooling coil is a heat exchanger, and if the design is a 15-degree delta T, like in this case here, a 50-ton air handler needs about 80 GPM. At 30 tons, in theory, it's supposed to be 48 GPM, but because the efficiency loss occurs at a lower delta T, you actually need more water than that. You need 24% more. You're going to need an additional 48, additional 12 GPM because of the change in efficiency of the heat exchanger. Now, there's another thing that happens that is a real bummer. The coil on the left, airflow is going from left to right. We've got 57-degree water going in down at the bottom, or coming onto the coil, pardon me, and 45-degree water going into the coil. The air going in from left to right moves across, and you can see the dry bulb going down to 52 degrees, something like that, 52.4. And you can see the water content, the red line, starting to drop off little bit in the 4th row, a lot in the 5th row, and also in the 6th row. Removing lots of water in the last coils. That's normal. Around 1.4 million BTUs sensible for 48,000 CFM. When you move over to the right-hand coil, same airflow, 48,000 CFM. And now we got a delta T issue on the coil. It's now a 5-degree delta T. 45-degree water going into the coil, 50-degree coming out. Well, if you look at row number 3, the water temperature is 48 degrees. On the other coil, 48 degrees occurred in the second, 5th row. Now it's in the 3rd row. Well, that's when water is going to start coming out of the coil at 48 degrees because of the condition of the air. So the dry bulb temperature is still 52 degrees as a dry bulb control, but because the coil is so much colder as a whole, it's going to start to dehumidify more, and you're going to start to pull more moisture out of the air. So even though this is a sort of reduced load, the delta T is lower, you're actually pulling more water out of there, and the total BTUs there's 100,000 BTUs more that you're pulling out of that coil at a lower delta T. So just running at a lower delta T just wastes energy by dehumidifying more than you need to. So what we want to do is we want to find a way to vary delta P throughout the year, and we change that delta P in response to things that are going on inside the loop. And this is one of the things we're going to talk about in a little bit more detail today. So we want to use some valve position on the air handler. We want to use zone info, server load, things like that. Any sort of data from the zone or from the air handler that's going to give us some advance warning about what is happening inside the air handler. And so that's a little bit different from PID. If you look at that basketball player, he's shooting at a hoop, and it's going through all the time. But once in a while, he'll clank it, he'll hit the rim or something like that, and he'll think a little bit about what he was doing and realize that he's got to hold his hand differently, or he's got to make some adjustments to it. And so that is an adjustment after the condition occurred. That is typically what you see with PID. But what happens if you have something like that, where there's changing conditions and you're trying to meet those changing conditions? So we want to use something called feed-forward control. Feed-forward control says, hey, what is happening, not just at what I'm trying to measure, but what is happening to create changes in what I'm trying to measure? And we're gonna look at those things, and we're going to use those to inform us as to what's supposed to happen. And this is an example, or this is actually what happens in the control process. This is the graphic that we want to see. In this case here, it's from a hospital. Because of the nature of that hospital, we took all of the zones, but you don't necessarily need all of them. In a typical building, you'd probably use 16 or maybe 18 zones. East, west, north, south, the corners of the building, and then you'd pick 4 or 5 or maybe 6 zones inside the building that are crucial, or meeting rooms or something like that. And you pick those zones, and those are the ones that you'd monitor. And so this one looks at an air handler output call. That is 1, 2, 3, 4, 5th column in. And the output call is what's happening from the fan power boxes or the VAV boxes coming back. What are those boxes saying to the air handling unit? So in one case, that first line, we've got 52%, sort of moderate. As you move down, you'll see there's one that's at 86%. That's calling for a little bit more. And so that is a load on the air handler that the fan power boxes are saying, hey, we've got some load. Let's figure out what's happening, and let's try to bump that fan up and try to get more out of the fan, try to get more out of the air handler. There is some fan speed. That is a response to what's happening with the VAV portion, the airflow portion of the system. There's some issue with cooling valve, or we look at cooling valve impact. What is the valve position, and also what is the temperature of that air handler. So if things are happening in the zones and it's starting to affect what's going on with the air handler, that tells this system, hey, there are some things that we need to do with this to make changes in the delta P set point for the chill water loop. So in essence, what we're doing is we're taking load information downstream from the information loop at the air handler, and we're using some of that information to, in advance, make adjustments to the delta P set point in the chilled water loop. So in other words, we're taking out that overshoot and some of that overshoot and undershoot. And what happens with the delta P control is we make small changes in it by half a PSI or 3/4 of a PSI. We go up or down and we wait 15 minutes or so until the change in pump pressure has an effect on those air handlers. And we'll make another adjustment up or down, up or down, up or down. We'll change that set point by a PSI to half a PSI in that range. Just change it up or down slightly and watch that effect on those air handlers and see what we have to do to keep those air handlers satisfied. So we're really trying to get away from having a bunch of PID loops happily, waving up and down all over the place and eventually living with the outcome of that. And we're trying to use this information to inform how much water we want coming out of the chilled water plant. It affects the chiller quite a bit. That low delta T affects the chiller, and we want to really pay attention to that. That is the other thing that happens sort of accidentally. And I'm going to just move on to the next slide and show you where that's coming from. Right down at the bottom, you can see something called a sieve. That sieve looks like it's a perforated metal plate. Looks like a colander, and it's there to take any liquid on the downstream or the underside, whether it's oil or liquid refrigerant, and flash it into atomize it basically. If it's oil, it just atomizes it into a vapor. If it's liquid refrigerant, because there's a pressure drop, it turns it into gas. That sieve is not in the water stream. No water is in contact with that ever. So if you have a low delta T with a lot of liquid refrigerant left over, as that refrigerant is being sucked up into the compressor inlet, it hits the sieve and it flashes off. And with a system that's a low delta T, that sieve, again, not in contact with the water in any way, that sieve will become the coldest piece of metal in the entire system by far. And it will actually become the world's biggest wind instrument. Low delta T chillers are very noisy because of exactly what you're seeing there. So it's just wasted energy. Low delta T just wastes energy at the chiller. Reduces its capacity and things of that nature as well. And so you can see that here on the left, you can see that with a low delta T, 6-degree delta T on a design of 12, it's losing probably about 30% of its refrigerant charge and a refrigerating effect at the inlet screen. That's a lot. You lose 30% of a 1,000-ton chiller, you only have a 700-ton chiller, and it's just blowing it right at the inlet screen. So we don't like that. We don't like to see that. Now, this is a different kind of evaporator. This is a falling film evaporator. And so the inlet screens are off on the upper left and upper right-hand side. And they still exist, they're just in a different place. And they operate the same way. Falling film evaporators are more efficient than flooded evaporators for a number of reasons. But the downside is that no free lunch in physics. Minimum flow requirement on a falling film evaporator is 40%. So you need to have a bypass line in to make them work properly. Bypass line in the chill water loop. Otherwise it won't work properly. If you get down to 10% flow or 15% flow, you can't run that through this chiller. So some chill water flow rules. We don't send water out of the chilled water plant unless the zones need it. So you don't pressurize the chill water loop and have a high delta P set point and hope that it's going to work out for you. You just don't do that. You maintain enough minimum pressure to allow water to push through the chill water valves, and that can be down as low as, I've run systems down as low as 3 psi. The valves are mostly open. There's hardly any pressure drop across them, and 3 psi sometimes will work just fine. But typically you'll run it somewhere down to around 5 psi or so, and you know, that'll work just fine. This allows you to stage up and stage down a little bit better. You may want to increase flow when you're doing stage up and stage down operations, just temporarily increase flow, and control chiller demand when you're doing stage up and stage down. And then once the new staging condition has been reached, you after a few minutes just release it slowly and let it go back to equilibrium. We generally like to stage up and down based on temperature and percent chiller load for that reason. We don't really stage up and down on tons anymore. For another reason that you're going to see here shortly, it doesn't make any sense to stage up and down on tons. Now the third portion of this is now condenser water relief that we want to look at. And under condenser water relief, we want to look at colder condenser water. And that colder condenser water helps us get some additional chiller capacity. What it does is inside the condenser, we have some very hot gas, and by having colder water going in, we're removing that heat and turning it into cooler refrigerant quicker. And that helps us get to a point where we're, instead of having warm liquid going through an expansion valve and flashing a bunch of it off, we're able to just say, hey, let's flash just a little bit off because the liquid is cool enough. We've made it cool enough. There are some temperature conditions or weather conditions you have to be concerned about: temperature and humidity and sunshine. And so the way that we deal with that is that we look at a chiller plant, and we look at the energy use of the plant. So the total energy use of the plant, the chiller, the condenser pumps, and the cooling tower all together, we add that all up, and we record that. The BMS records that and keeps it in its memory, and then it drops the temperature of the condenser water down by 1 degree, and waits about 15 minutes for everything else to settle out, all the steel and whatever else is in the system to reach equilibrium, and then measures the total power plant use again after 15 minutes. And if the power plant use went down under the same cooling load, then you made a good decision, let's drop it down another degree. And if the total power plant use went up, you made a bad decision, time to go back up. And that will happen all day long. The tower water temperature will reset up and down all day long as the sun goes up in the morning, as clouds come and go, as the temperature changes, humidity changes, as it rains, if there's any wind that comes up, all those things that affect cooling tower operation. As those things all occur and make the tower more efficient or less efficient, you're able to take advantage of that and run condenser water temperatures up and down. Now we do also down at the bottom, you'll see a little square there with a pump. We actually do also control pump speed to try to make sure that you have enough pressure inside the condenser to push the refrigerant out and through the expansion valve. So when you drop the temperature down, because the cooling tower water temperature is going to drop down, and when that happens, the refrigerant pressure drops down. So when that occurs, we slow the pump down. By slowing the pump down, that brings the pressure back up. And so there's two things that are happening. The pump is making the pressure go up and down, up, and the cooling tower is making the temperature of the refrigerant drop down. Those two are getting closer and closer together. You're getting closer to saturation point, closer and closer together. We need enough pressure push refrigerant out, and we want to cool it down enough so that we're flashing very, very little gas off. So this is the case that we're looking at. Normal case is around 30% of the gas gets flashed off in the condenser to make a 40-degree refrigerant, around a third, 70-30 mix. Now, if we just drop the temperature down only, what you'd end up with is not enough pressure inside the condenser to push refrigerant out, and eventually the evaporator would empty out a refrigerant. It would get, pressure would drop down lower and lower and lower, and as that pressure drops off lower and lower, the pressure difference across the compressor bundle gets higher and higher, and you'll run into low end surge. So what we do is we still have that temperature going in, we still slow or get the condenser water temperature cooler, we slow the pump down, and now instead of losing 30% of our gas, flash gas, now we're losing about 5%. So that's how we get a chiller that's a 1,000-ton chiller running at 1,300 tons. We get some extra capacity out of it because it's a little bit cooler. There are some limitations. You can't, you have to have enough water flow going through the cooling tower for the dispersion nozzles or dispersion tray or spray heads to work properly. So you can't, in most cases, you can't really go below about 40% of max flow. And you have to have enough pressure in the condenser to keep refrigerant flowing. You also have to have enough water flow through the condenser to prevent sediment from occurring. And so generally that's you don't want to go below about 50%, maybe 40% is the low end, but around 50% is kind of a safer number. And the way that you pick that number is you do a tube count on the condenser bundle and look at the water flow rates and figure out, based on the sediment that's in the area, what's an acceptable flow rate through all of those tubes. And that'll tell you your minimum flow rate. So with that minimum flow rate, once you assume or figure out what that minimum flow rate is, that's probably going to tell you also how cold you can make the cooling tower water. And you'll find generally that in most cases that 60 degrees is a reasonable minimum, and dropping 60-degree tower water is a reasonable minimum, and somewhere around 50% of condenser water flow is going to be somewhere around a reasonable minimum. That can vary depending on your local site conditions, but those are reasonable numbers to shoot for. So why do we do that? Well, 85-degree tower water, you can see the sweet spot in the middle is right around 70% or so at 100% output with 85-degree tower water. Well, 65-degree or 55-degree tower water, we got 132% output. There's no reason for us to stage up at 70% anymore. There is no sweet spot. So if we had 55-degree tower water, we would run one chiller all the way up to 132%. We'd run that 1,000-ton chiller up to 1,300 tons and let it run all day. It'd be very happy, wouldn't be overcurrent, no problems with the chiller, nice good delta T, everything's fine. As the condenser water gets warmer and warmer because of the ambient conditions, we're going to start to think about having that switch up point move back towards the idea of switching up at around, instead of switching up at 95% at 55-degree tower water, we'd tend to switch it at 70% or so with 85-degree tower water. So we're just taking advantage of that additional cooling capacity that Mother Nature's given us. Now the last one we want to look at here is fault detection, and this is a pretty good example of how fault detection works. This is off of an air-cooled chiller. It's got 3 compressors in it, and in this case we're monitoring something called delta P over P. So we're looking at the condenser pressure and the evaporator pressure. We're looking at the difference between those two, and we divide that number by the evaporator pressure. And when you look at that number, that calculation, if you come up with a number that is less than 2, you're going to be fine. You have a pretty good chance that the charge is okay. When it starts to creep over 2, and it starts to get like 2.5 to 3, then you can say, well, gee, you know, that things aren't looking very good. And when it gets to 4, you know that you have a chiller charge problem. I generally will say that if that number is around 3 to, you know, between 2.7 to 3, then you know you have a chiller charge problem. And that's just, there's no magic way around that problem. If you don't have enough gas in the system, what's going to happen is that the evaporator is going to become starved because it's trying to cool down the system enough, and the evaporator pressure is going to drop off. It's going to get lower and lower, and that delta P number between high side and low side is going to get bigger and bigger and bigger, and you're dividing it by the evaporator pressure, which is getting smaller and smaller. So it creeps up pretty quick. And that is a sure sign that you have a refrigerant problem. And this will, you know, what we'll do is, in this case here, and another similar cases, we'll notify, we'll have the system send out an alarm, and then when the service tech shows up, we just tell them that, hey, we were monitoring delta P over P, and it's way high. And so that's why you're out here. So he'll start looking around. And this chiller here, turns out that there was a leak at a service valve. Not a big deal. But we caught it long before there was a problem. I think he added, that was a 500-ton compressor. There were 3 of them in there. So it was a 1,500-ton machine. It had 800 pounds of refrigerant in it, total charge, and it was down by about 30 pounds. So we were able to pick that up pretty quickly. In the case in the lower right, chiller thermal efficiency is just a way of looking at how well the system is performing from what is its rated kW per ton at the condition that it's running at, and what is its actual kW per ton at the condition it's running at. You've seen chiller curves. They look at, you'll notice that they have varying outputs at different condenser temperatures and also different capacities. So that's okay. That's a curve. We understand those numbers, but we just take that polynomial, stick it into the BMS, and then we measure the actual value at that condition, and how close is it operating compared to what it's supposed to operate at. And in this case here in October, we had a chiller that was starting to have a problem. In that case there, we had a same system, but in October what had happened was that it had a problem with an expansion valve that wasn't working correctly. So just wasn't allowing refrigerant to flood through the system properly. So you can see how that using the information that we have and the information from the vendor, we're able to say what's its rated efficiency for the condition that we're at, and what is it actually doing. And there's a number of other fault detection routines that you can use, but those are pretty simple ones to get set up. So you keep it working by using fault detection, chiller and system fault detection, and you do pump and VFD maintenance on them. Look for system enhancements and calibration, and try to do some M&V once in a while in the system. I really think that that's very important. That M&V is pretty important. And just want to take a look at the system quarterly. How's it doing quarterly? Particularly, let's go back for a second. Things like thermal efficiency, system thermal efficiency, chiller thermal efficiency, valve fault detection, chiller fault detection, things like that. We want to look at that quarterly. How well are these things looking, and how much time did they spend in fault and things like that.
Okay, so to me, what I learned here, I mean, some of the stuff was beyond me, but some it's like, wow, I didn't realize this. My initial question before you start speaking is, why would you reduce the condenser water flow? You know, if it's on a VFD, I never understood why you would want to reduce the flow. Well, now I understand why, and that's and what'd you call it? You called it the condenser pressure is not enough. And is that what it is? The condenser in the chiller itself, the pressure is too low.
Right.
Yeah. Okay. So
Chiller guys call it lift. You need the lift is the pressure between the evaporator and the condenser. You need about 5 psi for that to work.
okay. And okay. My question is there, this is a simple question, and probably most of these people know this answer already, but I'm going to ask anyway. Do chillers usually give you or BMS systems, do you see that? I don't think so, right? Where you can see the lift or the delta P, you don't, right?
You can, so you can get that through a serial connection. That's a possibility.
But generally it's not in a BAS or a BES. I don't think I've seen that.
Yeah, and so we've all struggled with BMS contractors, and you know, trying to deal with those fellas makes me grind my teeth some days. I used to be one of them. And so the simplest way, you know, hey, there's a service valve on the chiller on the high side and the low side. These days now, all I say is, hey, let's put a pressure transducer on the high side and the low side at the service valve, and plug that into the BMS, and you've got 2 pressure points. That is not so hard to deal with.
Okay.
But you can rely on the serial interface if you're confident that the BMS guys are not going to lose it for you.
Okay, here's another question. Suppose you're in a situation where you're not going to get that. Okay, you're not going to get, the client's not going to give you, JLL runs buildings, so you get to play with controls, but we're consultants, we don't often get to play with their controls. And so I'm wondering, could you make some, not rule of thumb, but ballpark type estimate of, well, look, this is what I would do. If you have a condenser water reset, you make it down to 60-degree condenser water temperature, then you might want to reduce your flow to 40%, and then maybe go linear up to, I don't know what, maybe up to 70-degree. And then there you might be at 100%, and then from there on you just stay at 100%. Do you have any kind of rule like that you could use?
Yeah, and that's you're pretty close. There's not the amount of money that you're going to save below 60 degrees is just not, it starts to become more about artistic merit then. So 60 degrees is a pretty good drop off point. There's still some savings below there, but not a bunch. And if you have a condenser pump speed going down to 55% of max, then that's pretty safe, and you can make that. What you can do is you have leaving condenser water, or you have leaving chilled water and leaving condenser water temperatures off of there. You can monitor that and try and maintain that temperature difference, and use that to control the condenser pump speed, right?
Okay, so
You
you're saying, yeah, we look at the leaving chill water, leaving condenser water temperatures. We look at that delta T, and then use a relationship between that and the flow rate of the condenser water pump.
Yep.
And what can you give me, like, what kind of numbers I should use? So I got 55% flow. Well, you said it was 60-degree condenser water temperature, so maybe that might be what, a 28-degree, is that right? 18-degree T, maybe 55% flow.
Yep. Yeah, if you maintain 20-degree difference, you're going to be fine.
Okay. And then, but what would be the high range, assuming that's a linear relationship? Would it go all the way up to condenser water 80?
Probably go up to like 40.
Yeah,
right?
40. And then you would have 100% condenser water flow, and just go linear between those 2 points.
Right. But if you set the PID control for that pump at 28 degrees, what's going to happen is that as the condenser water temperature goes up, what's going to happen is that the pump's going to start pumping harder and harder and harder, and then as it gets warmer outside, naturally the temperature spread's going to get higher, and
Right.
the pump's just gonna try to control the 28 degrees and won't be able to. It'll just keep going up till it gets to 100%, right?
Right.
Which is fine. Yeah.
Yeah, that's
Fine.
okay, good. I'm okay with that. Okay, so the next question is, which is related to that, is that ASHRAE put out some guideline, or I don't know what it is, where they had all these controls, HVAC controls descriptions, or I don't know. They were supposed to be. I thought they were going to be just sequences where you can just copy them and paste them into something, but they're not. They're actually super complicated.
Right.
Did they address this in that book? Do you know?
I know they did not, and I've had several conversations with them about that, with various people in ASHRAE about that. But
Okay.
curiously, Tom Hartman, Optimum Energy,
Yeah.
any of the demand flow people, myself, none of us were asked to be involved in this. And in fact, a couple of us actually volunteered for it. So what ASHRAE is a pretty good group, generally speaking, but I would also say that in some cases, equipment vendors have a tendency to overrun that a little bit. And you can in the chiller control section, you can see the footprints of the chiller manufacturers in there a lot. There was a lot of, you can definitely see that. There's a Train in York written all over that. So
interesting. Yeah, that's something I wouldn't know. I mean, you would know because it sounds like you live and breathe chillers, but to me, I guess I'm a relative outsider. I mean, I know about chillers, but nothing like you. Okay. Here's a question from one of the people out there. So with the recent heat waves we're seeing in the South and other parts of the country, to the point where design conditions are being surpassed, and we're seeing more of that. So how do we maintain the system's abilities to meet these new conditions? Do some regions need to rethink their existing system or coil designs, or are there retrofits? Should there be redundancy? Have you thought about this?
Yeah, quite a bit. So we see that at JLL, and the first thing that I would say is I would want you to take a look at this very closely and look at the weather conditions very closely, and tell me when you see the actual weather condition exceed the temperature and humidity design condition. That hasn't happened yet, and I've been in Texas all this time.
All right.
We do see the dry bulb go up, but not the humidity. And so if you recall back from this presentation, you'll see that if you run into a delta T problem on the loop, you're starting to dehumidify way more than you need to, and you're wasting chiller capacity. So get the delta T under control, and you will stop wasting chiller plant capacity.
Okay.
Also, there is a side benefit to that. You're going to have better space humidity control and fewer temperature complaints inside the space. You're not going to have dry buildings where people are complaining that it's cold, and you're running around going, "But it's 72 in here." Yeah, well, it's dry, so so better humidity control is a good idea.
Okay. So what I'm going to do, if it's okay with you, I don't know what your schedule's like, Duane, but I want to go. There's actually more questions than I thought there would be. I want to go through them, and this time we're not going to stop on the hour, if that's okay with you. I didn't ask you if you can go over. Can you go over an extra 10 minutes or so?
Sure.
Let's go through them. So I don't know which chart he's talking about. He says, why does this chart show call set point of 85 degrees? Do you know what chart that might be? You might.
That one?
I don't know. Is there an 85 in there? Oh yeah, it says current call set point 85. Yeah, absolutely. So yeah, I don't know how to answer that question. So yeah, I didn't understand.
Current call, is it the output call? Is that what we're?
Yeah, if you go on the far right, it says call set point 85. Keep going all the way through.
Oh, I see. Yeah. So that is a number between that's a number between 80 and 100. So it's saying right now we're calling for the call set point's 85, the current call is 88. And so we're, what the system is gonna do is now the current delta P is 15, and it's gonna start to bump it up. So in the next 15-minute window, it's gonna change the delta P from 15 to probably 16. It's gonna go up more. So the call set point's 85, the current call is 88.
So you're trying to get to 85, right? So you're gonna bump it up to 85?
It's gonna try to get to 88. So the call set point stays constant for 15 minutes. The current call fluctuates up and down during that 15-minute window. And the system looks at it and says, so there's a number right underneath it that says what the past call was. Past call was 81.9. And so this, to me, what it's telling me is that this looks like a system that the load is increasing. So it increased in the last 15-minute window. I bumped it up. Now looks like it's next 15-minute window. It's going to bump it up some more, bump up to 80, bump the call set point up to, and it's going to change the delta P set point to 16. And eventually it'll get to the point where the delta P is high enough that the current call will start dropping down. It'll drop down to 80 or 78 or something like that. And then the delta P set point will drop down again.
Okay. Here's a question on the same chart. So someone wrote, I'm curious why in your example was the current delta P 15 so far from the set point of 35?
Well, you caught me on that one. This is a Excel spreadsheet that is actually live. And so when you use it as a tool, you're gonna put in all the values that are inherent in a system, that are in the system in the BMS. But you got to remember that the BMS is actually getting data coming back from it all the time. The Excel spreadsheet is not. It's only what you enter. And so sometimes when you're fooling around with it, putting values in, you get you can get that. You can create a condition in Excel where it's not following the natural world. That's just a mistake on my part.
Okay. Here's one. Is there a way to estimate losses from scaling, fouling, by seeing the evaporator condenser approach temperatures?
Yes. And both manufacturers, Trane and York, actually have information in their engineering manuals that describe that.
And so what these manuals are just online, you can just go download them?
Yeah. And I'm trying to think of the rule of thumb. I remember the Trane one. It was a percent scaling for every 1/10 of a degree off of its design difference from approach. So if the original approach was 2 degrees and it's 2.2, then you have like 2% scaling, something like that.
Okay. All right. And how do you look up? I didn't know about these manuals. How do you look these things up? What?
So Trane has a thing that you can use if you're a consultant. You get your local Trane rep, and you have to sign up with him, and he'll give you access to the Trane consultant website. It's the same one that consultants and contractors use. And you can the nice thing about it is you can plunk in the serial number for the chiller, and it'll bring up the original document, original submittal document,
Nice.
and all that kind of stuff. So all the original design manuals, things like that for that chiller, and all the approach temperatures and all that kind of stuff. And York has JCI has the same function too. They have the same tool, but you gotta go to the rep and ask them to sign you up.
Good. Okay, here's one. Is fault detection pre-programmed, or does it require a technical review of general system outputs?
Fault detection definitely requires, it is not pre-programmed, and they're boy. So let me just say that the fault detection that you see offered by BMS contractors is very much like a rainbow. There's stuff all over the place that is really good and some that is really bad, um, and typically most of it tends to get turned off after a few years. So it's very much the kind of thing that you want to be involved in from a commissioning point of view, and look at that system and make that fault detection for that particular building and for that particular system. You want to so the delta P over P number that I gave you, or the delta P over P formula, is pretty straightforward. But I would want to watch it in operation for a little bit and maybe tune it a bit, and before I turned it over to a client and said, yeah, this is finished. And so it's very much a tailor-made thing.
Here's another question. Can you increase the plant efficiency by stripping more heat from the condenser water feed through a heat exchanger to some process heat in the building? Let's see. Or will that add to many competing variables and not be worth the investment?
Sure. If you got a constant,
That's kind of clever. Yeah.
If you got a constant heat sink, then sure, why not? No reason why not.
Yeah, I think that's really clever. Okay. Yeah, so that's right. So then you're just saving on tower fan energy, kind of, right?
Right.
Okay. Really appreciate the quantification and relationships between delta T, flow, and performance. For all the material out there on optimization, this was the most concise I've encountered. Thanks. Can you expand on the method for resetting chill water temperature and flow in tandem? Ah, that's good. Yeah, that's good.
So this is chilled water flow. So generally speaking, we're trying to maintain. Let's go back here. There you go. We're trying to maintain. We're gonna reset chill water pump speed down to a point where we're getting close down to a minimum of somewhere around, whatever the minimum is, somewhere down around 5 psi. Let's pick a number and say that it's 8 psi is the minimum. When we start to get down to 8 psi, then we're getting to a point where we've got valve positions that are somewhere around 80 to 85%, and the valves are going to be starting to close off. And that's the point where I would start to think about raising chill water temperature up, and then reset it up and continue to reset it up. Again, the same sort of thing. I'm going to reset it up so that I can get the valves to open back up. And once we get to a point where the valves are opening up, then that's as far as I'd reset it. No point in having water flow out of the plant if you don't need to. So.
Okay, I might have spaced out or not heard this right, or maybe I did. So he was asking about also the chill water flow. So you're talking about the chill water reset, but how do you mix that with the flow, the chill water supply, the flow rate of the chill water?
So that's a good question. So we don't actually measure or control off of flow, and there's some reasons for that. The current methods being used for measuring flow are long-term or unreliable. I have yet to see a flow meter that is going to stay in calibration for longer than a year. And most of them don't last longer than 4 months. So using them as a flow point or a control point is very problematic. They're interesting pieces of information, and I might rely on them a little bit for fault detection. But I also, if I have to be really assured that we're going to provide consistent chill water performance for the rest of the building, I can't, I just don't worry about it. I do want to make sure that I got enough pressure to make sure that the chill water valves are functioning correctly. If I'm around 85% to 95%, then my delta P is in control, and whatever the flow is, I don't actually really. It's not that I don't care, but I find it an interesting point, but not something I'm going to worry a lot about. If I'm down at minimum delta P, then and the valves start to close off, then yeah, I'm going to reset the temperature up. But I'm not going to worry about what the flow is in order to do that. It's not a concern for me.
Okay. Here's another one. Have you looked at coil efficiency from fouling? With low delta T driving more condensing in the center of the coil and water causing more biofouling in the middle of the coil, have you seen a relationship?
Yeah. The low delta T really causes a problem with biofouling in the middle of the coil. It really does, and it is a, let's go back to that one. It is a serious problem. So the outside coil, the two outside coils, coil number 5 and 6, you can clean with steam or water, or you can use a foam. But when you start getting into row 3 and 4, you can't really get in there with foam. And if you try to do it with, a pressure washer, you just bend the hell out of the fins on the other coil. It's very problematic, and there are instances where I'll look at that coil and really there's only a couple of choices for them when it's really badly fouled. Well, 3. The real risky one, which is cracking the coil open and sort of bending the sections open so you can actually get inside. I don't recommend that because it tends to pop and snap all kinds of things. The other choice is replacing the coil. And then the last choice, which works, but it's very pricey, and that's putting UV filter on the outlet side of the coil, and that will clean the coil over a 2-year time period. It will do it, but it is very expensive to do, and so if you're in that spot, I've seen a lot of efforts to try to clean that, and most of them are not successful.
Okay. Here's one. How do you convince the facility operator to lower condenser water temperature, that lower condenser water temperatures are acceptable? They're always worried about oil migration or the lack thereof at low condenser water temperatures.
That's a very good question. And all I would respectfully do is if you recall, I pointed out that the manufacturers have a website that you're going to have access to and you get access to. All of the manufacturers have some form of head pressure control. They all do this. They all do condenser water temperature reset.
Okay.
They don't do it they don't do it in any way that's integrated with the rest of the building, but they all do it. Now, Train Earthwise does it. Train has something called Earthwise. York has CPO 40 or something like that. They all do it. So yeah, they all do it.
Okay. For what it's worth, the heat recovery potential is very low unless one has a need for lots of warm water around 80 degrees or less. Yeah. Okay. Right. Okay. Yeah. I guess that's a response. You know what that response is to.
Right.
Okay.
Right.
You have experience with chill water flow meters that are electromagnetic, that don't have moving parts. So you were talking about how these flow meters go out of calibration.
Yeah, I sure do. There's a very specific requirement for those any flow meter, There's a very, very specific requirement for upstream and downstream piping conditions. That is the first problem that you run into, and roughly half of the installations I see don't meet that requirement. Whether it's mechanical, magnetic, Coriolis, what have you. Next problem is what is supposed to happen with them is that they are supposed to be calibrated at a variety of flow conditions. From minimum flow, generally the manufacturers recommend 5 to 6 points between there and maximum flow. Haven't seen that yet. And I've looked at well over 100 of these things. Last problem. Once you get them calibrated, the requirement for these things is that they have to have a grounded power connection, and typically the power sensing, or sorry, the sensing array that's inside of there, the electronics, are very sensitive to ground voltages. And usually what happens inside of a chiller plant is that the ground voltage creeps up and down, between -5 volts, sometimes up to as much as 12 volts DC. And so then the flow meter goes out of whack because of that. So the power supply is kind of crappy. And so now sometimes that will actually cause the device to go into some kind of weird fault mode, and it'll produce some crazy numbers and just sit there. Other times it just produces bad information.
Okay, that's good.
Flow meters are the cocaine of the controls industry. That is an absolute fact. People love to push them, they love to use them, and they love to rely on them. Unfortunately, long term, they're just not reliable. They just aren't. So, wish they were, but they aren't.
I don't know if cocaine's the right word for that, but cocaine is ridiculous. Okay, when resetting condenser water temperature, I think you said you do it based on, okay, there we go. I think you said you do it based on plant kilowatts. How does that account for changes in the plant load? In other words, if the plant kilowatt increases, it could be because the change to condenser water temperature was not helpful, or because the load itself increased, right?
Correct. Yeah, that is correct. And you have to, that adjustment has to take that change in plant chiller load, plant cooling load into account.
Okay.
That is absolutely the case. And the control loop has to do that. It has to take that into account.
Okay.
And that is a commissioning function. That is truly a commissioning function. So while you're on site and you're looking at it, and you're looking at a change in the cooling in the chiller plant load, how much effect does that have on the operation of the condenser system? Is it if the load goes up 10%, did that increase the condenser loop power use by 10% or 5% or 4%? And it really depends on what is in the building and what's been installed. And you're going to have to, when you're doing commissioning, you're going to have to look at that and make that judgment call and determine how much that change in load has an effect on the condenser loop section.
Hey, that's it. We made it to the end of the questions. Look at that. That was a lot of questions. You guys, you're a great audience. You really like this stuff. I'm pleased we found something that really you guys are eating up. Duane, you did a great job. You're just a great communicator. I really appreciate your being on with us and staying over even. That was great. Thank you so much. Do you have any last points you want to make before we call the day?
You guys have, Mark, you've tipped me over the edge on this. So one of the things that I'm going to do with this is turn this into a series of YouTube videos.
Oh, cool.
So typically this is a 40 to 60 hour class.
Oh my God.
And so who has time to sit still for 40 hours? But if we chop it up into a bunch of YouTube videos,
right,
then that's a lot easier to deal with.
who teaches this stuff? I mean, who besides, I mean, you teach it, but who do you teach it to? If you do teach it, and who teaches it, and who goes to these classes?
So we have a bunch of people in JLL that take this class, and there's other contractors that will sit in on it from time to time. And there's enough of demand in it that I think it's worthwhile to do this. And who teaches it? You know, so a lot of the the demand flow people or
Yeah.
other people like that, they kind of hold this pretty close to their vest because they think it's a patented product and things like that.
Right.
So we take a different view. I take a different view of it, and JLL takes a different view of it. So if we continue to innovate in this process and continue to open it up to people, what's going to happen is that as a group we're going to get smarter, and and the product will actually get better.
Right.
So for instance, pump staging is something that we do now. We do handle pump staging very differently than what we used to. Just a short little spiel on pump staging. Now what we do is we set the system up so that we change from one pump to two pumps, and we measure what the current draw was before we switched and what the current draw is after we switch. And we see whether or not that was a smart decision. And if it was not a smart decision, in other words, we went from one pump to two pumps and the power use went up, the BMS, we programmed the BMS to make an adjustment and change that pressure switch point down, that speed switch point down, until it makes sense and we're making it at a good point. So if you're thinking about how a system curve works, the system curve at variable flow, that system curve is always different, and that pressure switch point is always going to change a little bit. And so we have that pressure switch up, that speed and pressure switch up and switch down. We have that moving up and down in the system all the time to take advantage of that change in the system curve. Now we found that out. We found that whole thing out because of some conversations we were having with a user that was looking at how pumps work. So this whole process of keeping everything open to people and going through the training process, we get information back from that,
Right.
and it helps us make the product better.
Right.
Right.
Does JLL offer these classes, this 40-hour thing?
Internally we do. I don't know if we've done it externally.
Okay.
But
That's what
I'm,
I was curious. Okay, because I'd like to send one of my engineers to, but if not,
and so that's the thing that's one of the reasons why we want to look at doing this as a series of YouTube videos, because it's too hard to get everybody together in a class. It's almost impossible these days. So, and the cost is crazy. But a YouTube video is pretty easy, right? So.
Yes, it is. Absolutely. Yep. Thank you so much. This was really great. Thanks for coming twice. All I can just say is thank you, thank you, thank you.
Yep.
Thank you.
It was very good for me too. Thanks very much.
All right, guys. Thanks for coming. See you next month.
Take care, everybody.